everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, we have started a new module, that is the radiation space environment, and in the last class we discussed what is radiation, what does it consist of. So, as I said, that is the radiation is basically that is the energy transfer. So, energy transfers, it can be by means of energetic particles or the electromagnetic radiation. So, we discussed those topic, then we discussed the different types of the classifications for the space environments of our interest. So, as you remember, we discussed this Earth's radiation band, that is the source of where we get the very energetic particles, and then we discussed about the galactic cosmic rays, and the third one which we discussed, which plays a profound role in the that is the spacecraft operation, that is the solar energetic particle events. Okay. So, today we will go ahead with further topics. So, we will discuss in today's session what is ionizing and non-ionizing radiation, and in regard to the ionizing radiation, we will discuss mathematically what is linear energy transfer, then what is total ionizing dose. So, it is also called this in short form, generally they put it, it is called LET, and this is TID. And when we will discuss those things, we will also discuss what is the stopping cross section and the stopping range. So, now let us discuss what is ionizing and non-ionizing radiation. So, as I already said, this radiation, this is consists of the high energy, the protons, electrons and the heavy ions, and they lose energy as they interact with the materials, and that process can be ionizing or the non-ionizing. So, when the radiation that has enough energy to move the atoms in a molecule or cause them to vibrate, but not remove electrons. So, that is referred to as non-ionizing radiation. So, here the effect is there, but that effect is not in terms of the ionization, but it can be the heating of the material, or there can be some atomic displacement. Those things can happen, but the material does not get ionized. So, examples of this kind of radiation are the radio waves, then microwaves, visible light. So, these are the types of radiation which does not cause the ionization. So, as I said, the non-ionizing radiation, it can produce damage in material and tissue by the production of heat or atomic displacements. On the other hand, ionizing radiation has sufficient energy to remove the bound electrons from the atomic structure. So, thus creating ions and charge distributions. The examples are X-rays, the gamma rays of these are the ionizing radiations. So, ionizing radiation, they can cause the malfunction of electronic devices, materials, especially the semiconductors. It can damage the tissue and it can cause a variety of radiation sickness, including cancer. So, that is why the manned missions, especially this astronauts and they are in the space station, the spacewalks, the radiation is a very important topic which need to be understood and proper care has to be taken. So, that you can minimize the exposure to the harmful radiation, especially the ionizing radiation. So, now we will have some mathematical treatment to understand how that is the ionizing, that is the radiation particles, they interact with the atomic structure and create the ionization. So, we will consider a single charged particle, and as a charged particle, or this is called a very high energetic charged particle moving at very high velocity, that that moves through a matter or a target, we will call that a target, it will pass close enough to the ambient atoms, and because of that thing the electrical forces become significant. It is something like the Coulomb force of attraction. You are having a charge and another atom, so there will be the force of the force will be exerted on the atom. So, that one will now see how we can do it mathematically. So, let us consider the interaction between a charged particle of mass m in kg and its velocity is meter per second and an atomic electron of mass m e. So, we are considering an atom where there are the orbiting electrons, and there are so here we will be mostly interested in the that is the outermost electron of the atomic structure. So, let us assume that B that is this velocity of the that is the radiation, that is the charged particle, and that is approaching the particle that has passed before the atomic electron and has moved appreciably. So, since we are considering the charged particles are having very high velocity. So, we are considering that those the particles, it will pass before the atomic particles moves, means always there is the probability that these energetic charged particles will catch up the atomic electron or that atom which it will interact with. So, pictorially it is shown like that. So, this is the charged particle here, this is the charged particle, and it is moving with a velocity of v, and this is the atomic electron, that is called the target, this is the target. So, the R represents the, so if you consider this as the origin, then this R represents the position vector, and this is the velocity vector, and we will say, we will explain what is A. So, you can see here that the particle is not, it need not move along the position vector of the particle, that is in that direction. It can move in any direction, but there will be an approach height, means there will be, even if it is near, there will be the interaction. So, at any instant there will be, since it is a charge, so there will be the electrostatic force between the two particles, and that I can represent it by this expression. So, this is basically the Coulomb force, and this is q 1 into q 2 divided by r square multiplied by 1 by 4 pi epsilon 0, where Z E C, this is the charge of the incoming particle, and R m is the distance of separation. So, this is the R m means meter, this is in meter. So, as I already said, in most of the cases the path of the approaching particle will not directly intercept the electron. You can see it from here, it is going in this direction, and the particle, so apparently it is not intercepting the atomic electron. So, you can calculate the distance between the particle and the atomic electron. This is expressed in terms of a distance of closest approach here. So, this is the distance of the closest approach, this one. So, if you consider a line passing a horizontal line parallel to the v vector, then the distance between these two lines, this is given by the this, and here you can write it because your A by r is equal to sin theta. So, you can write r is equal to A by sin theta, where theta, this is the angle of theta. So, this is the velocity vector and the vector connecting the particle and the electron. Now, we will use the relation between the force and momentum. So, what is momentum? P is equal to mass into velocity, and the force is m into acceleration, means force is F m dv by dt. I will put this as F, then it will be clear. Okay. So, then you can write this P is equal to, so dP by dt is equal to F, dP by dt is equal to F. So, P you can write integration of this F. Now, F is here since the force, since the particle is moving in a direction or it is getting accelerated in a direction which is which makes an angle theta. So, we have to take the component of that force, that is f sin theta. Now, if you define the coordinate axis such that the approaching particle has an initial velocity aligned with the x axis, that make use of the relation, then I can put x is equal to minus a cot theta. So, why it is so? Because the particle is moving in this direction, not this is the not particle is moving in this direction actually. So, this you are calling it the x axis, this you are calling x axis, and this is the vector which connects the point between this that is the initial position of the particle or the reference. This is the reference, this is the charged particle, then this we are calling it the approach distance. So, apparently what it should happen? It should happen, this is a, it will exert a force in this direction. So, if this is theta, this will be minus theta. So, this is x, this is a. So, you are having x, a by x is equal to minus tan theta. So, you can write x is equal to minus a cot theta. So, now, this is the Coulomb force between this atomic electron and the moving charge particle. So, this already we have seen, this is r is equal to a by sin theta, then x is equal to minus a cot theta, and then I can write the v is equal to dx by dt. So, this cot theta of differentiation of cot theta is d by d theta of cot theta is minus cos x square theta. So, I can write it like that. So, this will be, and then p is equal to given by this. Now, if you substitute these equations, then you can remove the term r using all these expressions. So, you can utilize all these equations and the momentum gained by the that atomic electron, you can write it in this way. So, what you have done, you have put all this this value to here and then this b. So, I can put this r is equal to r square is equal to s square by sin theta, then you can put from here. So, you can write in terms of d theta by dt in terms of b and a, and then you substitute into this expression this f expression, then you can show this is the final expression for the momentum that is gained by the target particle. Now, here we will take an approximation here just to relate this expression with the kinetic energy gained by the electron in terms of the equivalent temperature. So, as you know, that is I can write half m v square is equal to k T, and this is the this is the thermal, this is the temperature of the particle, or it is the T, I can say the equivalent the thermal energy. So, this is possible when I write this is not a relativistic, the velocity v is much lesser than as compared to the velocity of light. In this case, though this approximation seems very crude here, but still we assume that the velocity is not a relativistic, the effect is not there, means the velocity is much lower than the fraction of the than the velocity of light, and in that case I can express this T. So, is equal to this expression. So, P is equal to m square v square. So, T is equal to get so basically it is T means it is k into T. So, now you see, now we have expressed these terms. If you put all those terms here in terms of the P, then you can write the. So, this is the momentum gained, or you can say this is the energy transfer from the charge particle, moving charge particle to the atomic electron. So, now this is the expression already derived. Now, what you can do, you can put this here half m e v square. So, half m e v square, what does it mean? M e is the mass of the charged particle. So, that is basically the kinetic energy of the that high energetic particles which we have considered, which is interacting with the atomic oxys, that is atomic electron. So, now you see this expression, if you put this here, you put it like half m e v square is equal to E, then it will become 16 pi square epsilon 0, then S square, and this you can write E, where E is the that is the energy of the charged particle. So, now what does it mean that this is the original energy, now this energy has been imparted to the atomic electrons. So, now because of it has attained the energy, so which will become ionized after gaining only a few electrons. So, this is the electron bolt which is required to excite or to throw away the outermost electron. So, what does it mean? This means that this has become ionized because of this. So, what is that energy and what is its velocity and all those things, what is its approach distance, all these thing will and what is the charge, everything will decide this energy transfer. So, this energy transfer, this is a measure of the amount of energy that is used to ionize the target material. This is important. Okay. So, now this is the expression already we derived. Now, let us define a few terms, very important terms, that is called the linear energy transfer, LET. What is LET? So, LET is defined as the change in kinetic energy per unit path. So, this is the change in the kinetic energy or the energy which has been transferred by the. So, what will happen, this energy the energy of the approaching element or that is the charged particle or the radiation particle, it will lose its kinetic energy, and that is given by this function t. So, if you take the dt by dx, what does it mean? That it is the change in the kinetic energy per unit path length, and this is called the linear energy transfer, LET. So, what is LET then? LET is the amount of energy transferred per unit length of the particle's path, and this is its unit is kilo electron volt per micrometer. So, this is the this unit used for it. So, high LET radiation, it deposits energy more densely along its path. So, again it depends what is the energy, and it can cause the concentrated damage to cells or the particles or the material which is exposed to the high energy radiation. So, examples of high energy LET radiation, it can be alpha particles, the neutrons. Examples of low energy LET radiation, it can be X-rays, gamma rays, beta particles, electrons. So, that is why this X-rays are used medical, because it is a low LET radiation. Too much exposure to X-rays is also very harmful, but when you do send not very seldom if the X-ray images are taken, it does not cause any problem, because it is having low LET radiation. Now, let us see what is the another term, very important term, that is called the total ionizing dose. Let us define that one. So, here the change of kinetic energy per unit mass. So, that was per unit length, here it is per unit mass. So, this is called the total ionizing dose. So, total ionizing dose, it refers to the cumulative amount of ionizing radiation energy absorbed by a material or any electronic device over time. So, by TAD we understand this, what is the long term, or what is the that is the degradation of the the material degradation over the time. So, that is the TID. So, the SI unit for TID is Grays, or it is called GY. So, 1 GI is equal to 1 joule per kg, but this is a unit called the rad. So, rad means it is radiation absorbed dose, RAD. So, RAD is the conventional unit used in the space industry. 1 rad is equal to 100 arc per gram, or you can write it in terms of electron volt. So, it will be 6.24 into 10 to the power 13 electron volt per gram, or that is equal to 10 to the power minus 2 Grays. So, 100 material is equivalent to 100 arcs absorbed by 1 gram of the target material. So, this is the meaning. If I say 100, so 100 means it has absorbed 100 arcs of the radiation by 1 gram of the target material. So, now because the energy transfer per unit path length is dependent on the number of atoms which is encountered per unit path length. So, that is why both the TID and LET, they are dependent on the target density. What is the density of the atoms? So, that will define what is the TID and LET. So, it depends on the what is the number of the atoms it is getting encountered per unit path length, that is the TID, and then what is the the mass, again it depends on the density. So, that is why the TID and LET are they are dependent on the target density. In addition to the target density, the energy transfer is dependent on a parameter that is called the stopping cross section. We will try to understand what we are saying is stopping, or we will see another term called the range. We will now try to understand that. So, you can define the this is the sigma stop, that is called the stopping cross section. It is given by the integration of, that is the differential, or that is the change in the that is the that is the kinetic or the transfer of energy multiplied by the that is that differential area of the target material. So, so delta is the amount of the kinetic energy lost by the particle when moving through an area of dA of the target material. So, the cross section can be thought as the probability of, it can be thought so the cross section can be thought of as the probability of removing a given amount of energy from the charged particle. So, you can using this definition, so we can define the, that is the linear energy transfer, that is the LET, by this expression. So, dt by dx, so that is equal to this n sigma stop. So, what is n here? N is the atomic target density. Okay. So, this is the LET in terms of the, that is the stopping cross section. So, the now we will define a term that is called the range of the charged particle in the absorbing material. This can be, you can calculate it by integrating this equation. So, just let us see. So, we will define R is equal to, that is dx R to 0. So, R means then the energy transfer is T, when R is 0, the energy transfer is 0. So, we can write this expression R is equal to R to 0 integrating dx. So, this gives me R, and this, so I get minus T to 0 dt by n sigma stop. So, based on this thing, there can be the theoretical expressions for the stopping cross section. These are available, but it is preferable to estimate this sigma stop, that is the stopping cross section, from the empirical data. Empirical data means you have some measured data and you synthesize that data using the regression and all those things. So, if you do that, then the resulting range of the protons and electrons in aluminum, it has been done for aluminum, and we will show it in the subsequent slide, and we explain what is the meaning of the range and these two terms. So, this is a figure, you see in the y axis, it is the particle energy in mega electron volt, and in this x axis it is range given in centimeter, and these are the two curves. So, this linear one, the straight one, is for the protons, and wherever this zigzag and this not a non-linear thing line is for the electrons. So, this is the charged particle range in aluminum. Now, let us see what is this. So, you can note that suppose you consider this is 10 mega electron volt. So, if you see, the range, So, if you see the range for the energy, you know, particle energy, suppose if it is a particle energy is 10 mega electron volt, then it's having it's a, you know, the range for the electron is more than that of the proton. This is because the initial velocity of the electron will be much higher, because the proton has higher mass. This already also explained when we are explaining the, that is the spacecraft charging, that is the electron and proton, there also we said. So, this is this much, you know, that is the mass is higher, which means that it will have a velocity, that is electron will have a velocity of 43 times faster than the proton. And this mass difference also gives rise to another fundamental difference between the way which protons and electrons interact with matter. So, this is you can see from here how these two are different. When scattering atomic electrons, the more massive protons continue in essentially in straight lines until stopped. So, it is, you know, it is so somewhere it will stop, means it will impart all the energy. So, in that case you see for the proton it is straight line, whereas for the electrons it can be scatter, it can scatter of electrons, and they may be deflected through you know, the large angles. So, that it can happen because of electrons having the lighter mass. And so, electrons will, you know, the bounce around the inside the material until it is stopped, whereas the heavier materials, it will bounce, it will move in a straight line. So, this bouncing has been accounted for in the measurements of the stopping cross sections. So, the range data presented in these figures are interpreted as the depth of maximum penetration and not the path length. Okay. So, although the range particle is a function of target material, so as the first approximation, this dependence on material type can be ignored, and the particle range can be expressed independently of material units of length times density, that is gram per centimeter square. So, you see how it is instead of centimeters. So, what has been done, this has been the density has been multiplied with that thing. So, that you get, you know, this density gram per centimeter cube multiplied by centimeter. So, you are getting gram per centimeter cubes. So, it is the same part, but you know the range unit has been changed here. So, the range unit here is gram per centimeter square. Okay. So, this figure is illustrates one of the most obvious techniques used to protect spacecraft or its crew from the radiation environment shielding. What it says that if you put enough mass between the radiation source and the target, radiation will be absorbed by the shielding and will not be able to reach the target. So, these are called the radiation shielding. Okay. So, radiation shielding means it is used so that material will absorb the radiation before it can reach to the target material. So, here he has shown the lower energy particles are more easily stopped. So, you know this, if you see that stopping distances. So, for lower energy you will find that, you know, this low energy particles they are having lesser, you know, whenever the energy is low, their stopping distance are also less, and you know, as a result it is fairly easy to shield out the kilo electron volt or even mega electron volt energy particles. So, these are the majority of the particles found in tapped radiation belts. So, for the tapped radiation belt radiation you can use the shielding, but in the case of the giga electron volt energy, like we will see that GCRs, there are no shielding will work, and they will directly enter into the spacecraft. We will discuss how this, you know, how very energetic particles in the range of giga electron volt they affects the spacecraft. There you cannot use any type of shielding. So, I will end here and we will continue with this topic in subsequent sessions. Thank you very much.